Hey everyone, welcome to week 11 lab. So today, since we've already we had Dave's videos from last week, we're going to upload another one that he's doing today, Friday, that's just going over topo maps. We have the midterm next week, week 12. So we don't have the topo map quiz next week, we have it the following week. But a few things, I just wanted to basically show you sort of modern day applications of topo maps. I was talking to Dave, and in basically I use topo maps a lot, but then as far as other mapping sort of things go, a lot of it these days in the digital era with GPS, it's all sort of built in. But I still do have to occasionally calculate gradients and slopes and percent slopes, doing my work, know where if say I'm working at a hospital with an emergency generator and a diesel tank, I need to be able to look at a topo map or look at the topography of the nearby area and know if that tank ruptures, where that runoff is going to go. So there are modern day applications, but that really help us with that. So I use an app called Avenza. There's a ton of free apps out there. Avenza is just the one that I use. I'm the most familiar with. But basically, when I go into the field, I can find certain features. I can mark it. Say I'm taking soil samples, or I'm drilling or installing a monitoring well in a certain location. I can use my phone and stand over the point and mark it. And then I can download that KNZ file into Google Earth and make my maps for my reports and go back and look at it. And I'll show you a little bit about that. So here we are, lab week 11. I'm sure you all found it. I put some little things because I want to get you ready for week 13 for the topo quiz. It's going to be a bit different from the rock quizzes, a little bit more involved. You'll have to do some calculating. A couple of big things. Slope and gradient are the same thing. They're the elevation change over the distance change. So you calculate, if we're at between points A and B, goes from 200-foot contour interval up to 400-foot contour interval, and that's over a mile. If the gradient or the slope is 200 feet per mile. Additionally, if you're asking for percent slope, that percent sign should trigger you to remember percent. That means no units. That means I can't have feet per mile. I have to have feet per feet. So that 200 feet over 1 mile, you'll have to convert either the miles to feet, or you'll have to convert the feet to miles. Remember, 5,280 feet in a mile. That tells you, you see that percent? That tells you need to get rid of those dimensions and have it dimensionless. So you'll have feet divided by feet, and that'll give you a percentage. Additionally, know the map scales. A larger map versus a smaller scale map. Representative fractions is just that. It's a fraction. So 1 to 24,000 is a much larger scale map than 1 to 300,000. 1 over 300,000 is it's a much smaller fraction than 1 to 24,000. So that gives you an idea. Just think of those representative fractions as fractions. Those map scales give you a lot of information. Additionally, so you can think about it logically. So 1 to 24,000 means 1 foot on that map, or 1 inch on that map, equals 24 inches on the map in real life. So 1 inch on the map equals 24,000 inches in real life. 1 foot on that map equals 24,000 feet in real life. It's whatever unit you're measuring, that is what the representative fraction is. So if you think about it, on a 1 to 24,000 scale map, that 1 inch equals 24,000 inches. On a 1 to 300,000 map, that 1 inch equals 300,000. So you're covering a much larger area, which makes it a smaller scale map. Yeah, I think that's pretty much all I have to say. The PowerPoint presentation I shared last week and Dave's presentations last week go over a lot of this stuff. Know the features, saddles, know how to use the rule of V's to find the upstream direction of a river. Be able to find drainages, be able to find different topographic features, be able to use the contours to determine the change in elevation and we'll generally give you the distance. But if we don't give you the distance, there's usually a map scale, so you could measure it and figure out what the change in elevation is over the change in distance. So that being said, let's go here to Google Earth, and we'll start here with Mount Rainier. So Mount Rainier is a huge stratovolcano in the Pacific Northwest. I've got this GPS or USGS topo map, Earth Point topo map overlay. I put a link for it in the lab. If you're able to download it, that's great. I think this could be a lot of fun for you to just sort of interact with the maps and see how the topo maps basically show you exactly what is on the ground. You know, when I'm looking at a topo map, I'm seeing ridges and valleys, and I'm seeing mountains and hills. I've gotten used to it. I spend a lot of time looking at topo maps before I go into the field for a job. In teaching in school, I use a lot of topo maps, so I'm familiar enough with them that I can see these features. But this, I think, can be a really useful tool to show you what the topo map is trying to tell you. This way you can look at what the map looks like and what the topo map overlay looks like. So basically what I want you to do if you download it, you can go anywhere. You can go to the Grand Canyon, go to the not the Bahamas. It's just in the U.S., but you could go anywhere in the U.S., the Midwest, the East Coast. You could go to Yosemite. You can go to the Grand Canyon. All these different places and look at the features. So if you download the Earth Point, it'll be here on in your Places tab, but you'll click there to turn it on, and then you can turn up and down the transparency. So if you turn it all the way up, here we go. I'll turn this one off. So if you turn it all the way up, you should just have a topo map overlay. It's generating. Okay, so you can see the topo map. If you zoom in, it'll reorient to get to a different scale map. So as you zoom in, it'll go to a larger scale topo map. At least it should. There we go. Yeah, so you see the contour intervals changed because I zoomed in. It's moving from a larger a smaller scale map to a larger scale map because I'm zooming in. So basically the number of inches, 1 to 24,000, went to 1 to 1,600 or something based on me zooming in. But you can toggle the transparency over here if it's working. Okay, it's still thinking here. There we go. So if we turn that down, we should be able to just see Mount Rainier. And what I want you to do is go ahead and go down here under layers and turn on terrain. Otherwise it just looks, it's just a flat map. But if you turn on the terrain, it gives you sort of a 3D pop out. It's rendering, but you can then go down and get sort of a side profile and see Mount Rainier is this huge stratovolcano. But what I want to do here is just kind of give you an intro on what I'd like you to do if you can download this. If not, just follow along. You can look at different maps of topographic features and things like that. Or just watch this and get the idea. But I think it'd be really helpful to do it on your own and sort of explore and have fun with that. So if we look at Mount Rainier here, we know it's this huge stratovolcano. We can see the profile of it, and we can see these drainages, right? What would these look like on a topo map? Well, these are steep slopes, so we'd see a lot of closely spaced contour lines coming down. Down here in the river valley, it's moderately flat, relatively flat, so we would see more spacing on those topo and on those contour lines. You can see a peak here, another drainage that goes up this way, a drainage that goes up this way, a drainage that goes up this way. Because we see the mountain here, we can assume that this is uphill. We know that these streams are probably traveling this way. But if we didn't have the mountain in view and we just had, say, a topographic map of this area, we could take a look, and you can see how the topo lines cover that area. Like so right here, you see this is a peak right here. This is a steep slope going down into that drainage. If we open up the topo map, you can see, look at these lines, these steep lines right on top of it. We see them all going up. We see the peak right here. They're super close together. As we said earlier, look down in the river valley. These topo lines, here's one, here's the next one. They're very far spaced apart, so we know that this is a relatively flat area. We've got these super steep ones right here, these really close together. That tells us this is a hill. And then as we go up the creek valley, you can see there's one here, there's one here, there's one here. So it's a much the percent slope is much lower. The gradient is much lower than on these actual hillsides here. Let's just zoom out, or I want to zoom in a little bit and show you another thing. So if we look at a hill slope, there's going to be little drainages that lead to the main channel. So these are going to be tributaries that lead here. And what's nice is the topographic map can also show us these. So we've got a couple right here. Like these are water cut drainages in the side of this hill slope. We zoom in on the topo map and we can look. If we just had this bit, if we were just looking at this portion of map, how could we know that this was a drainage and which way was up? Well, look, you can see all these little arches, right? These V's. That tells you that the V points in the upstream direction. So this tells you that these drainages we're going up in elevation this way. You can see it in this rendering. All of these little arches are little tiny drainages that come down to the main one. You can see they all sort of come into all these little tributaries join the mainstream. If we look in the mainstream, we can also see here's the topo line making a V. Here's another topo line making a V. Here's the topo line making a V. It's Ving towards the upstream direction. This is upstream, and you can see all of these topo lines making these V's that point in the upstream direction. Same here. There's a V, there's a V, there's a V. That's very important. It always will V in the upstream direction. Let's see. What else do I want to show you? You can see you've got a lake here with a benchmark, 2577, or 4577, sorry. This lake is just sort of a little alpine lake that's up in the mountains. So I'm done with that. Just for fun, let's check out the Grand Canyon. So here's the Grand Canyon. Here's the Colorado River. But let's zoom in and see what we can see here. Let's turn on the terrain so we can get sort of a 3D view. Look at that. So we can see here's a drainage. Here's the main river. Here's little drainages, right? Let's see what that looks like without the terrain view on. And let's take a look with our topographic overlay. So we've got the river here. Unfortunately, this is a big enough river. It's always there, so the topo lines aren't crossing it because it's in water. So when you have a drainage that is sort of alpine, that isn't submerged, you'll usually get more topo lines. But we can see, we were just looking at those little drainages that are coming off of the cliff face. You can see right here, if we look at this drainage, where are these topo lines, these contour lines moving? They're Ving up in this direction. So we know generally, let's just say this is north, this is south. This river, the head of this river is up towards the north and it's running to the south into the Colorado. Same thing here. we've got another river right here. If we take a look at these topo lines, if these contour lines, here's another contour line. It's Ving this way. It's Ving this way. So we know that the uphill direction is towards the south. So it's running towards the north, generally towards the north, down to the main river channel. But again, the topo lines, these little V's that we're seeing in here, those let us know that that towards this direction is upstream and this is downstream, running into the main river valley. So another thing I want to show you, let's go local here. This is a job that I've been working on for a while. The Homeless Garden Project is going to occupy part of Poganip. They're going to build a new facility over here on the East Garden. Let's turn this down. Come on. Everything takes a minute to sort of catch up. Let's turn that off. Okay. So what we had to do is because they wanted to build a nursery, like a farm and nursery out here to expand the Homeless Garden Project. This is Poganip here. UCSC is right over here, but they're going to build here in the lower meadow. What we had to come in and do was first collect soil samples and do a geotechnical survey to determine whether or not that was the strata, the subsurface, was strong enough to hold the building. There's got the architects and geotechnical engineers come in, and then they take a look at the soil samples that we collected, and they run them through stress tests and shear tests. So basically simulating, like, okay, if there's an earthquake and we have pilings in the ground of this diameter and this sort of stress happens, this is how well this building would stand. And then they kind of use that to direct their plans. Additionally, we did what's called a phase 1 site assessment. It's an environmental site assessment where we look back as far as we can in history. We look at county records, city records, building records, environmental records, and we try to get an idea, aerial photographs. We try and get an idea of what this place was used for in the past to determine if we're going to run into any contaminants. So in that sort of historical search, the phase 1, we discovered that this used to be an old skeet shooting club. So this whole lower area, they had little standing places here, and they'd shoot the clay pigeons up in the air, and they'd kind of shoot uphill. So this whole area was covered in had lead contamination from the shells and the casings. So when we were out there, we did some soil sampling around, and sure enough, like we found shell casings, and we found lead in the soil. So basically, let me show you. So here is the boundary. Let me see, why isn't this working? Come on. If we turn this on, why isn't this? Bear with me for one moment. Hopefully this will populate really quickly here. Okay, give me 1 second. Okay, I'm back. So I just had to restart it. Sometimes when you're using all these layers and things, it can eat up memory, and it'll start to slow down. So one of the things that they had to do was they had to figure out exactly where they wanted their building to be. So here's the building footprint, where the boundary of their property was. This is going to be the garden boundary. And then another thing we had to do is we had to go in and do sort of a wetland survey and figure it out. Like, you can't really tell right here, but this is usually when you see green on a map, that means there's water nearby. This is a drainage. If we turn on the terrain here and we look like this, you can see the topography, right? You can see that we've got a drainage right here that comes down. You can see that the lower meadow around the drainage is relatively flat. So you've got the upper meadow and the lower meadow. And you've got this drainage here. If we look at the topo map, we'll be able to see the same thing. You can see that big drainage right there, right? So we can see that it's relatively flat in both of the meadow areas, like I said, and then we can see these V'ing up this little drainage here where all that greenery, all those trees were. This area right here, you can see, let's see if we can get the topo lines to show up. Look at that. So you can see right here, this is relatively flat. You can see it's just a slope. Here's a line, here's a line. But you can see that these start to V up because we've got a drainage here. So the topo lines are V'ing in the uphill direction. Same thing here. This is another sort of drainage that comes down by the road. We've got the upper meadow here, relatively flat. We've got this ridge right here. So that's another thing. Ridges. So there's a drainage here, which we see V'ing up, and there's a ridge right here, which make these sort of U shapes down. We look at the topo, yeah, you can see that, right? The ridge is sort of this rounded shape here, and the drainage, the topos come around the ridge and they V up in the drainage. Let me get back up here so our topo map will come back on. But we've got a ridge here and a drainage here. So we can see that sort of U shape for the ridge as it's coming downhill. But because the topo lines because the drainage is sort of cut, the drainage cuts away next to that hill. So the elevation on the hill right here, to reach the same elevation, if we just go straight across, we're going down into the drainage and back up. So in order to be at this topo line, in order to be at the same elevation, it's got to go way up here into the drainage, uphill, up into the drainage. That's why we get those V's. That's a really important concept that I want you all to keep in mind. So yeah, back to this. This is where they want to put the garden project. This is where they're going to have all their gardens. This whole lower area used to be a skeet shooting club with this whole area. So what we had to do was we had to figure out, okay, if this is your area and you're going to be digging in the soil and planting things, it's contaminated with lead most likely. We've got to figure out what is contaminated and what is not. So when we went in and we did a round of soil sampling, just sort of around the perimeter, and we started to see, okay, there's some contamination over here, there's some contamination over here. But also it's another thing that I was talking about with the app. When you're out there just hiking around, you take a soil sample, you walk away, it's going to be damn near impossible to find that exact same spot, which is why I use the app. So I collect my soil sample, I mark, sorb 1 on the map here, I mark sorb 1, B1, B2, whatever your designation is, and then you've got that file mapped to the GPS, and then I can open it up on the computer. And basically, so as we start collecting samples, right, we go around the perimeter, we're seeing this and that. But as we get these results back from the lab and we start to see that there are hotspots with higher contamination, then we sort of step out and get a more density in the area. So we get more and more samples. Like you can see this one up here was at 69. These ones are 60. or 16, 11. This one was at 50. So it just kind of gives you an idea. So we ended up doing a lot of samples here. That's not a sample. We also had to do sort of like a wetland survey, but this just shows you sort of where we were all doing. So these field tests, these have to do with the geotechnical borings. These green ones, these are sort of where they were testing we were taking samples to send to the lab to get an idea of the strength of the soil, how deep is bedrock, how are they going to construct this building, and then these red and blue ones are the ones that we were using to figure out where. So they're going to have a little garden over here. They're planning on having a garden over here and on this side, and so that's why we kind of focused on these areas. But yeah, we found lead. It was worse over here. So they had their sort of platforms here, and they were shooting up this way. So this is where most of the lead contamination was. Then we step out. Let's see if that shows up. No, that's not. Anyway, so that's basically what I do day to day. Is we have a site. It has some contamination. We've got to go check it out. Generally speaking, we started with basically turning this into a grid. So you take your area, you turn it into a grid, maybe 3 lines this way by 3 lines this way, and then you sample, and then you find out, okay, over here it's more contaminated. So then you step out north, east, south, and west from that area, and you sample those. And then if you find out, oh, it's more contaminated to the east, then you step out in that direction. So from that eastern point, you go northeast, south, and west. So you're kind of zeroing in, and then you get these nice little areas that okay, the contamination is most like right in here in these areas. So that's where you're going to excavate and get that soil out of there before people start digging in the soil and inhabiting it. A lot of our work's in San Jose. San Jose used to be all orchards back in the day. I can probably show you something pretty cool. We do a lot of aerial photographs looking at our perspective places. So here are some aerials. Back in the day, San Jose, like now, Silicon Valley, back in the day, it was almost entirely orchards. So this is our aerial photograph of a property we worked on, a commercial building. I think it was a dentist's office on Berryessa Road. And this is 1993, so it's more or less exactly how it looks today. But as we go back in time, you can kind of see how things have changed. So back in 74, that building wasn't there. It was croplands all around. And then if we go back even further, we can start to see here, back in 1940s, everywhere as far as you can see was all orchards. So then we look at this map. In orchards, they used to use a lot of pesticides, DDT, DDE, DDD, organochlorine pesticides, really, really bad stuff that we don't use so much today, but it was widely used back in the 30s, 40s, 50s. So I would use this information like, okay, back in the day, this was an orchard. Then I pull up a topo map, like, oh, okay. So I can see that the downstream, so here's a drainage right here. This is a canal. Well, now it's a canal. It used to just be a stream, a creek. But all the water, like so on the topo map, we can see all the water is running this way. So we know if there was something up, if we knew that there was a tank farm, like a diesel tank farm, or if there was one orchard up here, we knew that whenever it rained, it would probably rain and wash over our property. So we know that there's a pretty good idea that at our property, there were some upgradient contaminants that then flowed downhill over our property on their way down to this drainage. So yeah, a lot of times, like you look at a topo map now, and it's all developed. This is all residences and everything now. But back in the day, this was all orchards, and this was more of a more natural landscape. You can see the drainage is still here, but it's been channelized, sort of tamed. It goes underneath Capitol Avenue right here. But yeah, we use those topo maps to determine the spill potential, where things are going to flow. Also, it lets us know, sometimes you'll see that this drainage, this channel, it used to have it used to meander, right? Before it was channelized in the 60s. Maybe it used to come through our property. So we know that somewhere beneath our property is an old stream channel with sand and cobbles and pebbles they're more porous because they're big rounded clasts, and they have space, like pathways for water and contaminants to work their way through. So if we know that, maybe back in the 30s there was the stream channel ran underneath our property, we know that, maybe 10 or 15 feet down there is a old dried up stream channel there with a preferential pathway for contaminants to sort of flow beneath our property. But yeah, so that's just a little bit about what we're doing. I think I've taken enough of your time for this week. If you can, download this EarthPoint. It's really useful. It's super cool. I think it'll be very helpful to give you an idea of how to just sort of explore and figure out how these contour lines interact with the 3D features of the Earth. Like we look at, this is the SoCal quadrangle right here. Here's Santa Cruz, here's SoCal, but we can see the topo features. There's the Circle Church and the Circle area. Here's San Lorenzo, right? If we zoom in, we can see how the topo lines change on the environment. Not so much with with how everything's built up now, but you can also go back in time and maybe look at an older topo map if it's available. But yeah, play around with this. I can't recommend it enough. It can give you invaluable information. Plus, it'll, like looking over here, you can see that there aren't really any topo lines here, but you can see there's some steep ones right here. So we know that this is a hill that goes down into the San Lorenzo floodplain. All of this is floodplain on either side. It's very flat. But we can see that there's a steep. Here's those ocean terraces. Here's a little plateau, a little meadow area. It's steep over here. It's steep over here. It's more gently sloping down this way, but we can just follow it all the way up into the mountains, and we know that the San Lorenzo is going upstream because the contour lines are Ving across it up the stream. But yeah, I won't take any more of your time. Try this out. It's fun. Just spend 20 minutes clicking around, look at different things. Go to New York, go to Florida, go to the Grand Canyon. Look at the map, look at the terrain, and then overlay the topo, and then see how the contour lines interact with the environment. Yeah, I hope you guys have fun. Remember, next week we have the midterm 2. It's at the end of the week. And then the following week, we have the topo quiz. So practice, good luck, and we're always here for questions if you have any. So thanks.